Today we're going to be talking about representing exponential growth. So the first thing we're going to do is have a little math talk here about exponent rules. So we're going to make sure to rewrite each expression as a power of 2. So what does that mean? A power of 2 means that we're going to have 2 to some power being our answer. So if we have 2 to the third times 2 to the fourth, this actually means that we have 2 to the third, so 2 times 2 times 2, times 2 to the fourth, so 2 times 2 times 2 times 2, and all of that together will give us 2 to the 7th power. So the short way of doing that, instead of having to do this every time, is to just take those exponents and do what with them? Add them. Okay, so here we have 2 to the 5th times 2. That's going to give us 2 to the 6th power, because this is a 1 there. Okay, what happens if we have 2 to the 10th divided by 2 to the 7th? So 2 to the 10th divided by 2 to the 7th. What if we write it this way? If it's in a fraction like this, when we have exponents in a fraction, we subtract them. So this would give us 2 to the 3rd. And then our last one, 2 to the 9th divided by 2. Again, remember that's to the 1st. When they're in a division, you're going to subtract the exponents and get 2 to the 8th as our answer there. Alright, the next thing we're going to figure out is, what does x to the 0 mean? Okay, so the first thing we have to do is complete this table and see if we notice any sort of patterns that are happening. So here are values for x. We're going 4, 3, 2, 1, 0, and then we have 3 to the x. So this number here, this x value, is going in as the exponents. So 3 to the 4th power is 81. 3 to the 3rd power is 27. 3 squared would give us 9. You could also do this by seeing what pattern's happening. How are we going from 81 to 27? Well, we divide by 3. And 27 divided by 9. To get from 27 to 9, we would divide by 3. So to get from 9 to the next one, if we divide by 3 again, we would get 3. 3 to the 1st power is 3. And then here, to get from 3 backwards, again, we would divide by 3 and get 1. 3 to the 0 power is 1. Okay? So let's look at both of these here. It says, here are some equations. Find the solution to each equation using what you know about exponent rules. Okay? So if we have 9 to the question mark times 9 to the 7th equals 9 to the 7th, what does that question mark have to equal? If this exponent is staying the same and we already have 7, we know from our previous discussion up here that when you multiply things with the same base, you're going to add their exponents. So what number do we need to add to 7 to keep it at 7? So we would have to be having 0 as that question mark. Let's look at this one. We have 9 to the 12th divided by 9 to the question mark equals 9 to the 12th. Think about what happens when you have them in a fraction like this. We're going to take those exponents and subtract them. We need to take 12 minus some number to keep it 12. Well, what number is that going to be? Again, it would be 0. Okay? Because 9 to the 0 power is 1. If we take 1 times 9 to the 7th, we would get 9 to the 7th. 9 to the 12th divided by 9 to the 0 power is 1. 9 to the 12th divided by 1 is still 9 to the 12th. Okay, it goes back to this idea that if the 0 is the exponent, 1 is our answer. So then, what is the value of 5 to the 0 or 2 to the 0? If we have anything to the 0 power, it's going to be 1. So 5 to the 0 equals 1, and 2 to the 0 also equals 1. Alright, let's move on here. So we know, based on the associative property of addition or multiplication, that these two things are equal to each other. These two sides are equal. These two sides are equal. The grouping with parentheses doesn't affect the value of the expression. The answer is the same on both sides. Is this true for exponents? So, if we have 2 to the 3 to the 5th and 2 to the 3rd to the 5th, are those two things equal? If not, we need to know which one is bigger And which of those two would you choose as the meaning of the expression 2 to the 3 to the 5th written without parentheses? So let's just first start with figuring out what the heck we got going on. If we have 2 to the 3 to the 5th power, we would need to do this first, which is going to give us 2 to the 243 power. It's a really, really, really big number. Okay, you're taking 2 and multiplying it by itself 243 times. If we have 2 to the 3rd to the 5th, well, here if we have an exponent to an exponent, that means that we would have 2 to the 15th power there. Okay, so are those two things equal? No way. 2 to the 243rd and 2 to the 15th, not the same thing at all. But which of these two would you choose as the meaning of the expression if there were no parentheses at all? Okay, so this one's bigger. I'm going to put an inequality symbol in there. This one's bigger. That answers the first question. With this, we kind of work our way like backwards with this. So since there is no parentheses, it actually would be this over here. Okay. Most of the time, though, you're going to see some sort of parentheses happening with those to kind of give you that context clue of what makes sense, because obviously these are two very, very different questions to be dealing with. All right, so next question here. We're in a biology lab, and there are 500 bacteria that reproduce by splitting every hour on the hour. Each bacteria splits into 2 bacteria. Okay, so we're starting with 500. It says to write an expression to show how to find the number of bacteria after each hour listed in the table. So at hour 0, at our starting time, we have 500 bacteria. After 1 hour, each of those 500 splits into 2. So that means that we would have 500 times 2. Each of those is doubling, or we would have 1,000 bacteria. At the next hour, we have 500 times that 2 times another 2, because each of those 1,000 have split. So now we have 500 times 2 squared, because 2 times 2 is 2 squared. So we take our 1,000, we double it again, and we're at 2,000 bacteria. After 3 hours, we have our 500, and we're multiplying it by 2 to the 3rd power. Again, we doubled it 3 different times because of the 3 hours. Which means after 3 hours, we would have 4,000 bacterium. After 6 hours, so we are jumping a bit here, we would have 500 times 2 to the 6th. So we could type this in, or we could keep going from this and just go 3 additional hours. But after 6 hours, we would have 32,000 bacteria. Now, part B says write an equation relating N, the number of bacteria, to T, the number of hours. So here, we're going to fill in this piece. We want to know what would it be for T hours. Any number of hours we want to be able to figure out. Well, what's consistent about all of these? We're still starting with 500 bacterium. We also notice that each of these has a base of 2 there. That is our growth rate, our growth factor, because we're getting bigger. We're adding more and more bacteria each time. And then we're going to take it to the time, to the T power there, based on the number of hours that we have. Part C here says use your equation to find N when T is 0. What does the value of N mean in this situation? Okay. So if we were to plug in, if we have 500 times 2 to the 0 power, because our time is 0, well, we know that 2 to the 0 is 1, so we have 500 times 1, which means 500 bacteria to start. At time 0, 0 hours, we have 500 bacteria to start us off. So using that idea, let's look at this. In a different biology lab, a population of single-cell parasites also reproduces hourly But this equation given to us for the number of parasites P after T hours is P equals 100 times 3 to the T power. We want to explain what the numbers 100 and 3 mean in this situation. So what does that 100 represent? If you look up here, we can compare it. 100 is in the same place as that 500 was before. So that means that we have this 100 is the number of single cell parasites to start with, or at the beginning, or whatever you want to say. The 3 then, what is that going to represent? So this means that the number of single cell parasites triples every hour because it says hourly. Oops, I don't need to put hourly there. Okay, so that's our growth rate. This 3 is our growth rate because it triples every hour. All right, let's take a look at this in terms of graphs now. So we're going to refer back to our work in the table from those previous two. So here we had 500 times 2 to the T power, and here we had 100 times 3 to the T power. Okay, and we're going to graph those. So after 0 minutes, or sorry, after 0 hours, we had 500 bacteria. After 1 hour, we had 1,000. After 2 hours, we had 2,000. After 3 hours, we had 4,000. And after 4 hours, we would then have 8,000 if it doubled again. So let's see here. There we go. So each of those points, this was, we had 0, 500. We had 1, 1,000. 2, 2,000. 3, 4,000. And, 4, 8,000. Were those points. Okay? Over here at 0 hours, we would start off with 100. So since this is 1,000, each one's 250. So we're going to go about right there. And then at 1, we would be at 300. At 2, we would be at 900. At 3, we would be at 2,700. And at 4, we would be at 8,100. So up here. Okay, and again, you could have those same points as well. So again, we had 0, 100. 1, 300 because it triples each time, 2, 900, 3, 2,700, and then after 4 hours it was 8,100. Okay, so looking at these graphs, it's asking us here on the graph of n where can you see each number that appears in the equation. And same thing over here. So let's just look at this first one and answer letter number 2 there. So where can we see the 500? In this graph, where do we see that 500, that starting amount? So this is the y-intercept on this graph. At 0 hours, we're at 500. The 2 in the equation, we see because the y value of these is increasing by 2 each time. Okay, so y value increases by 2 each time. Now I'm not saying that you literally add 2 each time, you're literally multiplying by 2 each time as you go. And that's it for today.